Good evening, everyone. Can you hear me okay?
Yes.
Great, okay. Welcome to tonight's lecture. This is the 35th in an annual lecture series established to honor the teaching service of Sister Nora Harrington. Sister Nora taught chemistry and physics at the Elms for 32 years, and in that time built a tradition of excellence in the teaching of physical science. We offer these lectures to you to promote inquiry and scholarship, ideals that Sister herself embraced. Although Sister Nora has passed, her legacy continues. It's my pleasure now to introduce our speaker, Susan Corah. Susan graduated from the Elms in 1981 with a BA in biology. Shortly thereafter, she graduated from North Adams State College in 1985 with a bachelor's in chemistry. Her first job was working as a research scientist at Sprague Electric Company in North Adams. Throughout her professional career, she has worked as a research scientist, chemist, and process engineer for different companies, as well as a quality engineering consultant for different laboratories. She started at GE Global Research in 2004. Today, she is lead ceramic chemist at GE. She has an impressive record of accomplishment. She is the recipient of numerous awards at GE. In her professional life, she is the co-author of 5 U.S. patents. She will talk with us tonight about research at GE Global. The title of her talk is Structural Materials Development at GE Global Research. I give you Susan Corah.
Thank you very much, and thanks for being patient with my laptop. GE laptops are notorious for working extremely well in pressure-type situations. I'm sure you're all aware. So I'm going to talk to you about some of the work that we're doing at GE Global Research in Niskayuna on structural materials. Basically, structural materials are ceramics and metals, polymers, and composites. So we'll go through a number of slides talking about some of that and what the structure and mechanical properties mean. And then I'm going to shift a little bit over toward our aviation business because most of our structural materials organization focuses on the materials work that we do for aviation in Cincinnati and across the country. And there are some exciting developments with materials that have happened in the past couple of years. And then on the poster, there's just a little reference to when pigs can fly. We'll talk about a particular composite material that's 25 years in the making and finally is getting on some of the aircraft engines. So how did I get here from here? So 81 graduate of the Elms, great experience here. A couple of my classmates are here. It's great to see them. We're going to go out and eat something later. So from here I went to Sprague Electric Company in North Adams, Massachusetts, and I was working in ceramic dielectric development, so actually compositional work for materials that go into building ceramic capacitors and such. Also did some metallization type work because you can't have a capacitor without having some sort of internal electrode put in there too. The great folks at Sprague thought that a biologist was fine, but perhaps they would like to have some chemistry also, so they paid for my education at North Adams State College for chemistry, and then they sent me off to Rensselaer Polytechnic to do some graduate work there, which was really exciting and outstanding stuff. From there, in the 1990s, I worked for Heraeus Cermalloy, which is an ink house, and by ink I mean metallizations and ceramic inks that are designed essentially for screen printing patterns, so for semiconductors and some other ceramic arrays. And again, the metallizations are part of a screen printing process. I went to GE Global Research as a contractor in 2012 and became an employee in 2014. It's been an exciting road definitely. I started work originally in 2002 on solid oxide fuel cells, when back in the day those were ceramic materials, structural materials that we actually made into tapes and built, which this over here is a tri-layer system of anode, electrolyte, and then a cathode on top. Technology has changed dramatically, and by the time the SOFC technology moved forward, probably in about 2005, we were no longer working with these kinds of structures. It became extremely streamlined, and so this kind of was obsolete. So in 2015, I received an award as compliance champion for all of GE Global Research. And I have a passion for working in environmental health and safety to make sure that all of our folks, as I was telling Dr. Drake, you know, when you get home at the end of the day, you have the same number of fingers and toes that you did when you came in the morning. It's really a critical path and very important in pretty much any kind of lab situation. 2016, I took on some leadership with some of our global research STEM initiatives. We do a number of STEM initiatives over the course of the year with students of all ages. So we bring in high school students, we bring in middle school girls in a partnership with Niskayuna Schools during the summer to try to catch them before they get to high school so that we can try to get them to look into the math and engineering and technology stuff. And work with college level students also. And that kind of brings me to where I am today. I'm a lead ceramic chemist for my organization, EHS compliance lead, and our new organizational structure is called Structural Materials, and I'm part of Metals and Ceramics. So we'll talk a little bit about GE in general. How can you survive for centuries? So GE was founded in 1892 in Schenectady, New York, which is a stone's throw of where our GE Global Research World Headquarters is currently. And it was founded by the leading scientists of the day, Thomas Edison and Elihu Thomson and Charles Steinmetz. They essentially built this research lab in somebody's backyard garage. They decided that they wanted to have some sort of electromagnetic lab available for all sorts of innovations. So GE Global Research itself was founded in 1900, and it's been going strong ever since. We go through lots of iterations on things that we focus on, but currently we're doing lots of work in support of our GE businesses. So we have a very strong track record of innovation and invention. If you look at some of the things that have come out of the GE labs, 1879, carbon filament incandescent lamp, 1895, largest electric locomotive, 1896, first X-ray machine, 1941, first U.S. jet engine, and on through our 2014 with our record-breaking hot air gas turbine. So throughout the course of my talk today, I brought some show and tell pieces that are from various things. I have a turbine blade that's from one of these very large power generation turbines, and you're welcome afterwards to come up and handle them yourself and ask questions about them as after we're all done. So GE Global Research, we're the center of this circle. So I tell graduate students a lot of times when I'm working with them, because they're used to the kind of research that they're doing in their master's and PhD programs. If you see the word research in our sign, it doesn't mean that it's research for research's sake. We don't come in and on a Monday morning and say, gee, I thought of this over the weekend, I'm going to go to the lab and do this. We are business-based research. So if you see all the the things that our businesses here, power, aviation, healthcare, transportation, oil and gas, renewable energy, these are our customers. And at GE Global Research, we behave more like almost like a manufacturing operation, in that the businesses are our customers, and like any manufacturing operation, we have deliverables and goals that we have to meet. So where are we we're a global company. GE in general is a global company, but Global Research is just that. We have a global presence. So we have 2 core research centers. This is the world headquarters in Niskayuna, New York, and this is where I work. We have a sister center in Bangalore, India, and they do some similar parallel work to what we do at Niskayuna, but they do some different things as well. And then we have these focused incubation centers. Think of them as centers of excellence, where they focus very specifically. We're a very competitive R&D organization. So GRC was the first U.S. industrial research lab. So we recently realigned. We used to have a whole bunch of global research centers across the world, probably 6 or 7 of them. They found out, they realized we weren't focusing on the things that we needed to focus with all those separate entities. So this is what our structure looks like now: 2 core research centers and then the focused incubation centers. So what exactly are structural materials? So when you think structural materials, think of things that go into your cars or aviation parts, airplanes, body protection like, that's my dog. Excuse me, sorry about that. So let me continue to talk about it. I knew there was something I forgot to do before I got up here. And no, my dog doesn't exactly call me. So, primary purpose of a structural material is to withstand external forces. It's got to be a really strong material. So we're looking at the chemical and physical structures of those materials, and we're aligning them with certain properties and performance. So we're actually looking at mechanical type performance for these materials. So 4 examples of them are metals, ceramics, polymers, and composites. Composites are combinations of any of these kind of squished together. That's the technical term, squished. So what does our team look like at GE Global Research? So we have over 150 technologists that support structural materials. In Niskayuna, we have ceramics and metals, which is my organization, coatings, characterization, manufacturing, and materials behavior. The materials behavior guys are the ones who do all the mechanical testing to determine whether or not the materials that we're creating actually are achieving what they were meant to do. In India, we have folks that work on metals and coating, and also non-destructive evaluation and microanalysis. Excuse me. So we're going to talk a lot about high temperature materials today, and of 3 different groups: ceramics, metals, and coatings. So we use some traditional metallurgical techniques. For example, this piece of equipment, it's a 1,000-ton forging press. So this is the very old-fashioned way that we're making new alloys that are better and stronger. One of the cool things that we do when we bring in our school groups, this is in my building, actually. We bring them in, and we have a great team of people who volunteer to do the demo for this. So they get all suited up in their safety heat suits, and it's especially for the little kids, it's very exciting because they take a red hot brick out of an oven that's probably at about, a furnace rather, that's probably at about 2000 F or 2100 F. So it's blazing red hot. It goes into the forge, they apply the pressure, the thing just smashes down to a circular bowl, and they take it from the press and they put it in some cooling water, and steam is everywhere, and the kids are like, ah. It's very exciting. It's an old-fashioned technique, but it works very well for some of our processes. And this right here is, I can't be standing here in 2018 and not mentioning something about robotic technology. That's become very, very big for us. But these actually are thermal spray robots, and this is actually an aviation blade. We've gotten to the point with our materials, we can use this hot plasma spray and the two robots to actually get 12 degrees of freedom in which to spray our material onto the blade that's going to go into an engine somewhere. So it's very exciting stuff. So why are we talking high temperature materials? So if we're talking aviation, so imagine you're sitting on an airplane down at Bradley and you're getting ready to go somewhere. So there's 3 different conditions that we have to look at with regards to temperature. We have to look at takeoff, we have to look at climb, and we have to look at cruise. So it makes sense if you think about it. What kind of energy are you going to need on takeoff? You're going to need something that's very, very high energy, that is at a very high temperature. Temperature ranges on takeoff can probably be anywhere around 2200 F on those engines. And then consider climb. I mean, takeoff requires a lot of energy. Climb also is going to require quite a bit of energy. And then you get to cruise altitude. Now, cruise, okay, you've gotten to the point where at cruise altitude, your temperature is going to be a little bit less, but you're still going to be probably running about 2000 F. So just imagine the kind of materials that you have to have on these engines in order to be able to be stable at these temperatures. So one very important part of what we do in structural materials is, as you can imagine, we do a lot of material characterization, because if we're looking at structure property relationships, we need to be able to have data that tells us about composition, mechanical strength, and several other types of characterization. So internal capabilities, if we don't have them internally, you can see on the right, there are a few external partners that we work with, including a couple of universities. So if we can't do it on site, we have partners that we can work with. So we do imaging and analysis, and through that we can do some topography and chemistry of the surfaces. We do a lot of X-ray diffraction. We also can do structural analysis through X-ray diffraction. We study crystal structure to see what the best crystal structures are for these materials. We can do compositional analysis, because many of the materials we use, be it a metal alloy or be it some sort of ceramic thermal barrier coating or an environmental barrier coating, it's generally a mixture of materials, and it's good to have some compositional background behind us. We can also do thermal and mechanical analysis, and one thing, this is kind of a new thing for us, rheometry. Now, if you consider rheology, where we're measuring viscosity of a particular kind of slurry or an ink or a spray, that's kind of well-known concept to us across the industry. And there's all sorts of kinds of slurry viscometers, like Brookfield viscometers. Some of you may have used these either here or in your working life. A new technology that has emerged probably within the past 5 or 6 years is actually powder rheology, which is called rheometry. The pharmaceutical industry uses this quite a bit, and one of the basic important things that you get from the data on this is you get a measure of flowability of the powder. So in its raw handling, most things that we work with start in a powder form. So we have ceramic powders, or we have metal powders, or we have metal alloy powders. Knowing how these things flow is very important. So the particular instrument that's available now, top of the line globally, measures several different properties of a powder: flowability, tap density, bulk density, a lot of very valuable information. And for flowability, if you consider additive manufacturing, there are a couple of different ways that additive happens, but one of the ways is a laser melting process, direct metal laser melting. And in that condition, flowability of powder is very, very important because it actually has to flow down a feed tube and onto the platform, and a laser actually then will hit it and melt it. So flowability is very important. And the other thing we do a lot of characterization on is particle size and particle morphology, because, like I said, we start with powders all the way around, and it's important to know what kind of size particles you're dealing with in terms of how many microns is this, or how wide is the distribution. Sometimes we use that data as an advantage to help us design a structured particle packing for maximum densification. So. Okay, here we're going to talk just a little bit about two GE engines that are out in the field right now. On the left, this is the GE NX, and this is the GE 9X. So the materials that we use on these, very important alloys: nickel, titanium, and iron, and as well as combining them with different ceramics and polymers. So we talk about some of the process technologies here. There are castings that are involved with ceramics where we actually develop a mold that then is covered in wax, and we're actually able to use that model to make the metal castings for some of the blades. And I have, this is an actual ceramic casting of an engine blade. I'm not exactly sure which one it's from. It might be from the LEAP engine. But from this ceramic casting, we can go to a casting house and come up with this piece of an engine blade. Coatings are also important. We have two types of coatings that we work with regularly: environmental barrier coatings and thermal barrier coatings. Both of those coatings are meant to protect the alloy or the bond coat that's underneath it. So thermal barrier coatings are developed to be able to withstand very, very high temperatures, and ultimately will protect the hardware that's underneath it. I think a little later on we have a picture of that. The biggest new thing, and it's not new because it's old, it's our When Pigs Can Fly, it's a CMC, it's a ceramic matrix composite, and it's the latest, greatest thing now that it's on some of these engines. And what's important about it is being a ceramic material rather than being a titanium alloy. It's much lighter. So if you have these kinds of components on your aircraft engines, the total weight of the airplane or the engine is going to be significantly less, and thus your fuel efficiency goes up crazy big, and the aviation industry loves that. That's what they're looking for. And the other thing we do, we have something called repair here, and we're working on some in situ repair type scenarios. We have materials that are available now where when we do have an aircraft engine that comes in for inspection, if there are any defects in there, we have the means to go in and actually repair those on wing. Oh, and these are videos that don't work. I'll share them with Dr. Drake when I get back to work tomorrow, and he can share them with you guys if you want to see them. What these actually are, and I have to tell you, I watched them for the first time yesterday. This is a really sexy video of the whole, the engine, and it all like flies around in pieces, parts. It's very impressive. I'm sure you would have liked it if it would have worked. But I can pass those along to you if you're interested. So this is the third engine we're going to talk about. This is the LEAP engine. It was introduced in 2016. And what do we need to know about this? What's different about this? What makes it better? You got fuel nozzles that are additively manufactured. So through one of the processes that we use, whether it's DMLM or one of the other ones, it's 5 times stronger. And because it's built in one piece, there are 5 times fewer brazes and welds. So consider a fuel nozzle that's traditionally built. In order to put the whole thing together and make it very uniform, it's going to have to be brazed or welded to make sure that all the connections are made. But when you 3D print something like this, you don't have as many opportunities where you have to have a braze or a weld. So NOx emissions are lower. Everybody loves that. And this is the first commercial jet engine that uses the ceramic matrix composites, and we'll talk a little bit about how those are made. But it's 2/3 lighter than the metal equivalent. That's a lot. That is significant here. So here, it's designed to stay on wing for 8 to 10 years before the first major overhaul. That doesn't mean that they don't come in for inspection or what's called an outage, which sounds like a kind of really weird word to use, but there are scheduled outages for most of these aircraft engines in that as a determined schedule, determined amount of time when an engine has to come off and be inspected or replaced. But this is designed to last significantly longer. And there's your 3D printed fuel nozzle, and this is a CMC shroud. So what kinds of alloys do we use on these engines? So there are 4, nickel, titanium, cobalt, and steel. So the nickel alloys are found in the blades that are shown here and some of the rotors. We've got some nickel alloy seals in this part of the engine, and then high temperature nickel alloy for the blades and the vanes here. The titanium alloys are found, it's a titanium aluminide in the blades that are here, and then we've got a fan and a rotor that is the titanium alloy here. So cobalt, with the cobalt, this is the DMLM cobalt combustion. That's the direct metal laser melting portion. And also in the combustor liner, we've got high temperature cobalt alloy. And then on the last one, with the steel, we've got right here, the leading edge on the fan blade. So what's a leading edge? So the way the fan blades are put together, a leading edge is called the edge that actually sees the environment first when it's on an engine. Leading edge, if you'll think about it, that provides probably the best opportunity to have problems with environmental issues hitting the edges. So that if we have coatings, we may find that we have much more deterioration on the leading edge than we do on the rest of the blade. We have some novel coating technologies that I'll just go over very briefly. So critical to quality factors, the kinds of things that we're looking for, we need to have thermal conductivity, toughness, stability, durability, impact resistance, and erosion resistance. And the last one is CMAS resistance. Now, think about this. Think about an aircraft engine that's flying in the Middle East. There are different kinds of environmental factors that that engine is going to run into that you don't see if you're flying in the States or in other parts of the world. So essentially what CMAS is, it's a combination of calcium, magnesium, aluminum, and silica. It's a silicate is what it is. It's essentially a glass. And the problem is that it deposits on the engine blades and eats through some of the thermal barrier coating, and it decays it. So these are the blades, and this is a blade that's actually has a TBC coating on it. So if you see, this is a bare blade. This one has the coating. And this is a piece of hardware, same blade that's actually been fielded and taken off of an engine. So this is kind of how the composition goes on many of these parts. Here's your super alloy substrate, whatever we talked about on the slide before. You've got a bond coat here, which is actually just what it sounds like. It's bonding the alloy to this thermal barrier coating here, which is a zirconia composition ceramic material. So by putting this thermal barrier coating here, we can get to a higher firing temperature and reduced cooling air and a longer component life. So if you're thinking about this, you're like, well, Sue, you got this coating on here. How are you going to sinter something that's already on an engine? How can you do that? So what we do, we talked about the high temperatures, right? We use those temperature cycles in order to actually sinter the ceramic material that's on the blade. So no additional steps are needed. It's just something that sinters as the engines are cycled. Okay, like I said, we have to do a little bit of robotics here because it's 2018 and it's cool. So there is something that we have developed. It's called Turbine Surgeon. And these are actually little tiny robots that can be deployed inside the engine, and they're going in between some of these blades, and they're doing a different type of inspection. So tiny robots will inspect and fix jet engines from the inside. So this is part of my team. I work with these guys, and we do some of this. It's very, very exciting. And our robotics professionals that work here, they have the coolest little, they're called crawlers. They're actually little mini robots that can go crawling around in the engine and do an inspection. They also have magnetic crawlers, which are very beneficial if there's magnetic material that we're using there, because they don't fall off of the surface as they're going through. So it's a pretty exciting time for this. Are you going to go? Oop, sorry. One back. All right, so old inspection technology. This is a borescope. So it's basically a fiber optic on a handle. You turn it on, and you can, some of the engines, most of the engines are built, engineered and designed with borescope holes in them at strategic locations. So you can actually use this inspection tool. You go in, you maneuver it around, and you try to see what's going on inside between the blades. So that's old technology. So the new technology is that we're using the Turbine Surgeon. And this is another one of those videos that's not working. Sorry about that. But the robots go in and they can inspect shrouds and nozzles and blades much more efficiently than because you have to manually manipulate the fiber optic cable on this when you get it in. That's kind of difficult to do if you don't know what kinds of surfaces you're looking at. All right, And a little bit about ceramic matrix composites, CMCs. So back in January 2001, we're trying to figure out what kind of structural ceramic can you use in a turbine engine. So DARPA asked the Institute for Defense Analyses to do an assessment and see what the opportunities might be there. So the people that were involved in these discussions were many government agencies. And here's what they determined. So will any ceramics be on engines? And that was the title of their report. Will pigs fly before ceramics do? So what has happened since then, since 2001? So this was the first flight of an aircraft that had an engine that had ceramic matrix composites in it. And 2016 was the first delivery of an engine that had the ceramic matrix composites in it. So when pigs fly. I was telling them they should make little pigs with engines on the side. They would be great giveaways for talks like this. So what the report did for us in the first place, though, it identified a whole bunch of things that weren't being done at the time. So incomplete characterization, not great environmental assessments, and system integration. So we had to do a lot of work in order to overcome all this. So if you look at, this is a big timeline of revolution for ceramics, right? So here, 500 BC, okay, ceramics is art. It lasts a millennium unless you drop it, and then you have nothing, right? In the 1960s, missiles and rockets, and of course the ceramic tiles on the space shuttle. So I have one of those tiles here. This is a alumina silicate type structure, but it's not very dense. It's got a crystal structure that's very different. It's almost fibrous, and all that goes over these ceramic tiles on the shuttles from back then, it's just a 16th inch piece of aluminum that goes on top of these, and this is the whole insulating piece here. So where did we go from there? So now, 2016, we're in aircraft engines, we're in the LEAP, we're in the 9X. So things have come a long way, and they're only getting better because more ceramic parts are being produced that are going to go into engines. It'll make them lighter, and it will make them more fuel efficient. So ceramics as a whole, if you look at this timeline, 1990 to 1999, CMC via a particular process, it's called melt infiltration. There's a pre-impregnation tape. So the CMC as a composite is almost like a tape. And we'll go through a little bit of this. Here's our flying pig right here. Gen 2 EBC, this is an environmental barrier coating. A lot has happened since the 1990s here. And when we've gotten to the point 2010 and above, we're at our ceramic components in our jet engines. So what's a CMC? This is a really complicated system. This is why it's taken so long to develop. You have a silicon carbide fiber here, and it gets coated. It gets impregnated in a specific slurry of a proprietary composition, and then it's wound onto a drum, and then it has to be preformed, and then it has to be compacted, and then it has to be densified, and then it has to be machined and inspected, and then the EBC goes on top of it. So it is, it's a long time coming, but we own our supply chain, so we control how well that this does. So from imagination to mass production, we're imagination at work. We used to be, we brought good things to life, but I guess we don't do that anymore. We imagine. So we have gotten to the point where we've got scale up. We have our manufacturing facility that's in Asheville, North Carolina, and we've got advanced manufacturing techniques that we're using, including a bunch of robotics on this. This is a LEAP engine, a LEAP 1A engine. I was at Aviation last year doing some work. And just to give you a little perspective, it's one thing to see one of these engines actually on an aircraft. But when you're standing in front of one of these, it's pretty exceptional. It's pretty amazing. So the location of this particular shop, it's called CTEC, and it's at Aviation in Cincinnati. It's the Customer Technical Education Center. So every GE engine that is currently flying, there is a working model of them in this entire shop. It's a whole shop floor. And the whole purpose of this particular facility is for airline people to send in their repair technicians, for them to be able to work on repairs directly on the engine that they're going to see if they're in a hangar at an airport somewhere. And these classes run all day long, all week long, and repair techs are in all the time. It also gives us, though, an opportunity, if we have some innovative testing or something new that we want to try to put on one of these, occasionally they'll allow us in there and give us access to one of the engines. We can, at least if we're designing some different kinds of I'm trying to think what we're, inspection tools, we actually have the right geometry of the inside of the engine so that we can work directly with how it would be seen in the field. So it's a big thing. It's a big thing. So there's tons more we could talk about. My contact information is here, Corah@ge.com. I forgot all my business cards. It was quite a stellar day. But Dr. Drake will know how to get in touch with me if you want to, if there's anything else that you would like to talk about. Any questions? Thank you. Yes.
I have a question.
Yeah.
So you said you have patents on your, through your career, several patents. Can you just give us an idea of what some of those
Sure.
innovations-
Sure. I have 3 patents from the former Sprague Electric Company, where we were working on different sorts of dielectric composition based on what the capacitor need was. So different properties that we were looking at, different industry designations. So what you need to know about IP, it's very interesting when you're looking at patent space. If you're looking at it as a whole, it's when you're doing your initial research on what can you patent, what can't you patent. So there's a window around a particular composition. And it covers, perhaps in a ceramic compositional analysis, it covers a certain range, but it generally excludes points that are beyond that. So most of the time with IP, you're kind of working with something that's already been developed, but you're going outside the scope of that to see if there's more improvements in characteristics or whatever. And oftentimes that space opens up and it turns out that the first folks just didn't go far enough with their matrix. So those are 3 different compositions. And then I have one for, one of the most interesting years I had at Global Research was the number of programs that I worked on were so vastly different. I worked on NOx catalyst for emission reduction in a diesel locomotive. So there's one thing, and that spawned one of the patents there, and that was awesome. So that was one range of my year. The other part of my year was working on scintillator materials for the most recent high-definition CT scanner. Healthcare, transportation, and we're a little more focused now because I'm certain people have been reading about GE over the past couple of years. We're picking and choosing. We're being very careful about the kinds of technology we're going forward with. So healthcare is pretty much independent now. They don't request us as much to do any kind of work. Aviation, we do a lot of work for aviation across the center. So we're more centric there. The patent disclosure that just went through this year is for a dual-phase magnetic motor application that is a government contract for these magnetic motors, but this is also an aviation supported program. So I forget what the other one was.
Where do you see things going in the future? Is it maybe with composites and developments and those, or?
Yeah, I think it is. I think one of the slides that I ended up pulling out of here kind of late in the day today, so those CMCs that are now on those engines, we started working on those 25 years ago. So, and one of the things that we have to do at research, and what I think a lot of companies do, you're not looking forward to what your business, what does aviation want 2 years from now? We have to be looking 10 years ahead, because if we're not working on that now, we're going to be behind the game when we get further down the road. So CMCs, we have one gentleman who refuses to retire until he sees total success with the CMC program, because he's one of the innovators that put the whole program together back in whenever, 1990 or whatever it was. So nothing goes out to the business for to actually be put in production unless it's been seriously tested. So that same year I was working on those NOx catalysts. That's when that scintillator material got pushed out into the CT scanner. And just an aside, I had to take my daughter for imaging for something at the local hospital. Probably a year later, and I walked in, and there it was. And it's like, that is awesome. Now, in your career with global research, that's a very rare occasion when something that you're working with on the bench actually gets scaled up, and then to pilot plant, and then maybe to a vendor, and then gets out there. But the people at the hospital were very kind that day, because I walked in and I looked at it and I'm like, ooh, can I see how it works as a whole unit? Because I had worked on one composition of the scintillator material that's in the array that spins around. Very cool thing though. Yes, sir.
Does the patent work? Does the company own the patent, or do you share ownership and license?
Oh man, I wouldn't be standing here in front of you if I owned any of that IP. It's so in most cases when you go to a job or a company like GE, or I guess it's probably, you guys can tell me, pretty universal. Anything that you develop, you pretty much have signed away on your first day, on your day one employment application papers or whatever. It doesn't mean that you don't get recognition for it, or there are patent awards, moderate patent awards that they give these days, in the form of cash. But generally you're working on with a large team, and we have, at our site anyway, we have patent attorneys who work with us one-on-one. And interestingly, many of our patent attorneys at Global Research were bench technologists, they material scientists, whatever, and they had that expertise. And several years ago, GE decided the kind of patent attorneys that they wanted were the ones who had that technology background, so they actually sent these folks to law school with the understanding that after law school they would, I guess, I don't know what the agreement was, they would stay for at least 5 years. But how much easier is it to work with a patent attorney who knows exactly what you're talking about because they used to work on the bench? So, you know, when you're thinking about things you might want to do in your career, because one of the things I think about is how did I get where I am now from being here sitting in your seat a few years ago, right? And sometimes it's happenstance. Things happen and maybe you're not going to do exactly what you want to do right out of school. And maybe you're going to have a whole bunch of winding roads, but the opportunities are great. I mean, would I have wanted to go to law school? And that's really not my thing. But for these guys, working with those kinds of patent attorneys make everything so easy, and they're right on site. Anybody else?
Susan, the Southwest airline issue that happened this week, the metal fatigue in one of the engine blades, would that have been not possible, say, were that engine to have involved the CMC materials?
Because of where the CNC materials are located within the engine, I'd say no. This is we don't actually really know what happened with that. The CFM 5929 is a GE engine. They're out there all over the place. They're in tons and tons of 737s. It's a mature technology, but it's a proven one. The thing that has been bothering me, and this is not any GE standpoint, what bothers me is that an inspection was performed on that engine the day before. And that's where, without saying anything else, because I'm a peon in the company, so I can't say too much, I look at that as, how can you inspect it one day and have something like that happen? So, no, the CMC wouldn't have had an effect on that at all. But metal fatigue, that's pretty much what they determined, and on one of the titanium blades. So who knows? Don't know what to tell you on that. I was preparing for this question because I talked to my program leader yesterday. I said, I'm going to get there and somebody is going to ask a question about the Southwest engine. And I said, how do I respond to that? And he said, what you tell those people in your audience is that's why our jobs are so important. And that's why we work on a CNC material for 25 years before it goes onto an engine. It's our job to make sure the materials work well. So I don't know what happened with that, but Nancy.
Yeah, so can we just build on one thing? I was going to ask you, you talked about intellectual property. One of the big problems for many companies, whether it's a toy company like ours or yours, is that the research and the money and the investment that companies like ours put into technology, there's huge problems with that technology being stolen and counterfeiting and all
Absolutely,
this.
yeah.
In your technology, and again, from a safety perspective, you certainly, whether it's toys or jet engines, you have similar concerns. How is GE approaching, at a very high level, because it's a very complicated subject, but how is GE approaching maintaining, the integrity of its intellectual property and making sure that, particularly in some of the other emerging markets, it's not being leveraged against you?
So one thing GE is very adamant about is that if you're going to work for the company, integrity has to be number one. It's very important. And we have had people leave Global Research who have stolen IP, or they've taken stuff on, well, the one in particular a few years ago, an engineer left not only taking files, data, and a number of other things, but resigned on the spur of the moment and went to a competitor. Now, these are all no-nos. I mean, I don't think I need to tell you that that's wrong. So GE went to the competitor and told them what happened, and that person lost their job. And there were prosecution implications on that, because those confidentiality agreements that you sign on day one are legally binding, and that stuff belongs to the company. But, so from a high level, yeah, they prosecute if they catch them. So, but that is a problem, all over the place. So, I don't know if that answered your
Yeah.
question. Anyone else?
Do those confidentiality agreements give you as the individual any wiggle room if you want to work on a project in your basement or?
Okay, that's an interesting question. I don't think you have wiggle room on these. IP is IP, and if it's something that you do, and correct me if I'm wrong, Nancy, if, and I may be wrong, this may be true, is it anything that you invent while you are,
No, and I have kids who are in their 20s and are signing their first kind of contracts and think they're going to invent the next iPhone in their basement and are wondering, are they signing away their right to do that? It's usually structured around related to your job and your industry. So you'll sign that you turn over anything you create to your company. Sometimes though, to get to what you were talking about earlier, you also have to sign a non-compete.
yes,
Meaning that at least for a year or whatever, after you leave the company, you won't go into a direct competitor or something like that. So, but no, I mean, there's a lot of people that run side businesses, but if it's in direct conflict with their day job, that's a problem. But if you're an entrepreneur on the side and you're doing a day job, most companies in general are okay with that.
yes.
What if it's like not for profit? Like in academia, you're seeing a lot of people publish their findings to open sources, and you see, tech companies like Tesla and stuff, all their stuff is open source. Do you ever see, these large scale manufacturers like GE encouraging that kind of approach to research?
Short answer, no. No. Let's face it, GE's been around for going on 3 centuries now, and their policies are very strict. Like you asked, there's not wiggle room, those kind of things, so.
I think there's a competitor, Scranton Whitney is right down the road and is a huge competitor to GE in terms of engines, and you can see just a snippet of how much energy goes into creating this stuff. And you lose one account to Airbus or Boeing, I mean, it's billions of dollars.
Yeah, it
So
is.
in this level of technology, it's a little bit harder to be open source.
Yeah.
So the sheer cost involved.
So I know finals are coming. I have some stress reducers for you here. And the one thing I didn't show you, and I lugged it all the way from this Vienna, so I showed you the little blades, okay? So these are the blades that are on, like the 9X, the Gen X, the 9X, and the Leap, and they're small. I lugged it all the way from Schenectady. You gotta look at it, okay? This is a turbine blade, stage 1 blade from a power generation turbine. So this is designed to generate power. It's really big and it's really heavy, and it generates 43 megawatts. So if you want to come up and hang on to this one, and this has a bond code on it also. So I've got stuff up here if you want to look at it, put your hands on it, whatever. Dr. Drake can tell you how to get a hold of me if you have any other questions. Otherwise, thank you.
Thank you very much.